effect. Before that, let's just do some math. I don't expect you to be able to memorize it or derive it, but I think if you want to claim that you understand this cryogenic and some quantum effect, it will be good to know how to solve the Schrodinger equation in one dimension, right? For those who are from physics or MSQT, probably it's easy for you. But this is also simple if we are not scared. Just treat it as a wave, okay? A wave equation, okay? So how do you solve a quantum object? The governing equation is the Schrodinger equation, right? It's just like the Newton's laws in classical mechanics. This can be very complicated and has a lot of insights that we need to learn, but we are not studying this class because this is not a quantum mechanics class, right? But after all, this is the equation. Negative h bar square over 2m. I put star here. Divergence square of psi equal to E psi. Now, if you look at this, you probably get scared by it, but really doesn't matter. You don't need to memorize it, then you will feel better, right? Because you can Google, ChatGPT, Wikipedia. But you want to understand what it means. First, what is psi? Psi is a function of the position and also the time, and we call this the wave function of the object or the particle, the elementary particle, for example, electron, that we are interested in. We want to understand its behavior, and let's just take it for granted. Every object is just a wave, right? So we don't spend time to debate why it is so, right? It's philosophically debated for many years, over a century now, right? This Schrodinger proposed this equation in 1923. So just 100 years, right? Huh? I think it's around 23, 24. I forgot, right? Yeah, anyway, it's about 100 years. So we just accept this. So electron is no longer a particle in this view, but we will see that it has particle. I mean, we will not see, but in this class, but you could see that there's something called particle-wave duality. You can treat it as a wave or treat it as a particle to explain different phenomena. Anyway, this is the wave function. What you're trying to tell us is that what is the probability? I mean, the distribution of the electron as a function of the location and also the time, okay? Particularly, it is found that the magnitude square of this wave function is just equals to the probability, right, of finding the particle at a particular location. Right, and if for those who had taken E225 or who know the direct notation, if you don't know what I'm talking about, it's fine, right? If you did not take this class, but just to remind you, this is the wave picture, but this is just like the inner product of the cat and bra states, right? If you have taken this class, otherwise, no need to worry about this. So, but again, no need to memorize this. The point is why wave function is important, because it's magnitude square related to the probability that it will exist at the time, at the given time, and also the given location. And that's it. So you have a huge wave function, you have a large value at a certain place, then you can say it is confined to that place, right? For example, if I have this psi square of a particle, and it is like this, for example. It is basically saying that I have a very large probability of finding the electron at this location. I still have finite probability finding it elsewhere. Maybe this location is on this table, and this location is on your table. So overall, I can say, well, the electron probably is on my table, but there's a finite probability I can find it at your table. right? It's a wave spreading everywhere. Okay, so the whole purpose of this Schrodinger equation is that is to say that this wave function obey this equation. And what does it mean? On the left, it is actually referring to the kinetic energy of the particle, right? So this is not a full Schrodinger equation because we don't have the potential energy. We are talking about free electron. Free electron means the potential equals to 0. Okay, so it's infinitely large space. You don't have potential. You don't have positive electric field, right? It's just a free electron. So on the left, it is related to kinetic energy. On the right, is related to the total energy. Then at this point, of course, kinetic energy equals to the total energy. So the goal is to solve. If I give you this equation, you want to, what should be the form of the psi that I will satisfy this wave function, right? Now this is a 3D one, right? It might be useful just to remind you that what is the meaning of del square. This is just equal to partial square, partial x square, plus partial square, partial y square, plus partial square, partial c square. You should know this also, right, E student, because you use this in your EM class, right? You learned all this before. But just to remind you, again, no need to memorize, right? Just to remind you that you have this thing for those who are interested in this. And then we are only to think about 1D case. Let's say it is one-dimensional. Then this equation will be reduced to negative h bar divided by 2m star. Do you remember what is m star? Effective mass, right? Although now this is a little bit, you may say is contradiction. You're talking about free electron, and then now you say your effective mass is not the electron itself. But this free electron can be actually the free electron in your 2D gas, 2D electron gas. You can have a free electron in your quantum well formed by the silicon heterostructure, right? So we just putting m star for now, so that you can use it in any cases, right? So if you don't like that, just put m0, which is still correct if it is really free, right? So because it's 2D, I only need to consider partial square, partial x square, right? I don't have x, y square and z square, and psi of x of t equals to e of x of t. Okay, so basically we're asking for a 1D condition. What would be the form of this psi? Again, this is a wave of the electron, right? Is this okay? Do you feel comfortable now for the assumption that I make so far? Basically, you need to admit that, you need to accept that electron is a wave, right? If you accept that, are you okay that what we're solving now? And another thing you accept is treat this like F equal to ma, right? You accept F equal to ma, which you have daily experience, right? You won't challenge your high school teacher or middle school when they tell you that it's F equal to ma, because you do have this experience. Oh yeah, if I hit it, then you will accelerate. That is your daily experience. Difficulty of quantum mechanics is that you usually don't have the daily experience. Now it's better, you have a lot of animation on the web, right? You just look at some video, then you gradually feel that, okay, I have this wave, you need to satisfy certain condition, right? So now you accept it. First, you accept the Schrodinger equation. You cannot prove it. This is the fundamental equation, right? You only can check that if it works. And then you accept psi is the quantity we are interested in, right? So then it becomes a mathematical problem, right? Probably you learn in calculus or whatever. A general solution for this equation is what? is psi of t xt equals to a constant a e to the power I kx plus b e to the power negative I kx. Here basically is, and actually sorry, I'm not going to include the time factor here. Okay, so I only, we actually don't have the t, I'm sorry, because we are doing a time independent. At the beginning, I gave you a time independent one already. I should not have added this extra into the, this. I don't have this in my cheat sheet because this is not a time dependent Schrodinger equation. Okay, this is time independent, means it does not depend on time. Okay, because we already skip a step from the time-dependent Schrodinger equation, we already removed the t. So from here, you see that it has two waves. It basically representing one traveling to the left and one traveling to the right. And you cannot see it from here until we add the time-dependent part on it, which is e to the power negative I capital E divided by t. But anyway, let's just accept this, right? So now, then, how do you check that this is correct? Well, you either based on your calculus, you know that this is correct. If not, then we can plug in, right? We can plug in to check. So I plug in this equation. I have the negative I squared divided by 2m star, right? And then I have this partial square, partial x square. I plug in a e to the power I kx plus b e to the power negative I kx, right? And then I try to take this out. When you differentiate the exponents by 2 times, you just take the exponent out, right? So this becomes I k squared times a e to the power I kx plus negative I k squared times b e to the power negative I kx. Is this part okay? I did this one by x, right? So I take out ik. And I do the second time, I take out ik one more time. Then it's ik squared. Do the same thing, it's negative ik 2 times, right? So what is this? This gives me negative k squared. This also gives me negative k squared. Because negative times negative 1 is 1. And I squared is negative 1, right? So this whole thing is going to give me negative h bar squared k squared divided by 2m. And then when I take this out, then I have a times e to the power ikx plus b to the power e to the negative ikx, which is just equal to the psi of x. And sorry, because I already took the negative. This is negative. Negative times negative is positive, right? So again, I squared is negative 1. Negative 1 times negative 1 is positive, right? So that's why I have this. Is this okay? The left-hand side, I just plug in. Then how can I make this one? How can I make this equation? How can I make this satisfy the equation? Then you just requires E equals to h bar squared k squared divided by 2m star. If your energy equals to h bar squared k squared divided by 2m star, then you satisfy this equation. Okay? So basically, it is telling us what? It is telling us that if you solve a free electron, its energy is going to be equal to h bar squared k squared divided by 2m. And what is the meaning of this? If you think about electron in classical sense, a free electron, what energy does it have? Does it have potential energy? A free electron? No, right? Free means no potential, right? So what energy can it have? Only kinetic energy, right? So in classically, we also know that E equals to P squared divided by 2m, where P is the momentum, right? So from here you see that momentum is h bar times k, right? So we are not proving it. We just see the correspondence, right? It turned out that the h bar, which is the reduced Planck's constant, times the k, which is the so-called wave vector. Why is wave vector? Now you go back to here, I kx. This is extra. Okay, let's extra. K. Or let's think about this. What is e to the power I kx? Is equal to cosine kx plus I sine kx, right? So this is just like a wave, right? A periodic function, right? So obviously, k must be equal to 2 pi divided by the lambda, the wavelength. Because if you plug this in, you find that when x equal to lambda, then you have a full cycle. You plug k to here, if x equal to lambda, then you have a full cycle, right? Because it's cosine 2 pi and sine 2 pi. So that's why k itself, due to this formulation, is already the so-called wave number, which is 2 pi divided by lambda. This is called wave number. So what do you need to learn here? You don't need to learn anything. It's not within the scope of the midterm or final. But I really want you to go through to have a feeling about why we eventually come up with the momentum is just equal to the h bar times k. Okay, the Planck constant times the wave number equals to the momentum. You will see this very often, not in this class, however, in all the engineer quantum problem. Okay, but here point out one very important thing. The energy really depends on the solution. Okay, so that is first thing. Any questions so far? I hope you can relate the total energy to the momentum, right? But why I want to do this, right? Of course, it will be good to understand this, but more importantly, okay, actually this one not